But, you know, realistically, it's the last problem with the second test. You know, you might be mentally wiped by then, careless errors happen. So anyway, I gotta take my constants and I'm gonna bring them over to the other side, my 60 and my 12, actually my negative 60 and 12, I'll do the opposite, bring them over. So I'll end up with 48. And then I've got my, let's see, so that'll be negative 48, I added over, careless error. Where's the mistake?
The 60 and the 76 is supposed to be positive.
Yes. Because I'm distributing -5, and there's a negative right there, two negatives make a positive. And I know you just saw me make a careless error. That doesn't make it cool. So if I bring that over, then I'm left with 76.4985 minus 2.5428.
Which is 73.9557.
9557.
Yep.
I1 equals 48. Therefore, I1 equals
wouldn't that be -48?
no, because I've got 12 and -60, so on the left-hand side, it's -48, and then I add it to the other side.
I1 equals 0.6490.
Units?
Amps.
I assume that's what you're about to say, Jack, but your deep southern accent made it sound like an O sound. The famous southern unit of ohms. All right, we got one of them. We got more. Sorry, I was just not expecting to jump into the deep end like this, but it's introducing a lot of concepts that will bring down to a simpler problem.
So you said this would be on the second test. Will it be 5 unknowns? Probably.
No, it'll end up being 3 unknowns,
You should definitely.
or possibly 2, depending on how you do it.
Definitely make it 5. We've done it, we can do it.
I believe, I like that
You can
attitude.
give
I'll
Dan
do it just
5.
for you. Your test will have 5 equations, 5
Give him
unknowns.
6.
It's gonna have like a parentheses, test 1B, or Ibrahim.
It'll become a tradition, the Ibrahim problem. Although Jack's the one who said, just, you know, keep it as is, don't move the 1. All right, so I2 or I3, we have an equation right here for I3, so we can find I3. So my current flowing, first off, let's start marking down what we do know. I1 is the current flowing in this path right here. So that was 0.6490 amperes. I3, I know is 1.5428 times that. And I3 is across here. If someone would be kind enough to do that multiplication. It looks like they all believe in you, Ibrahim.
Okay. What am I supposed to, because when you drew the bottom red line, what is that referring to?
That's I3.
Oh, okay.
And I3 equals 1.5428 times our value for I1, which we know now.
Okay.
And now it's just sort of working backwards.
I3 is 1.0013.
1.0013?
Yeah.
Amps. This is 0.0013. All right, I5.
Now, quick question.
1.6503.
023.
No, just 3.
03. Yeah, Jack?
If we were to remove the 1, how would that help us? The 1 amp?
We could have done a complete reduction of the, we could have reduced it down to a single equivalent resistor. Figured out the current flowing out of this and then just sort of work back.
Oh, if there was an junction there, we could do a parallel.
If this had been here, this would all have been in parallel. Sorry, this would have, we have a parallel structure with this, that combination, that pig form. We'd have a series structure of these two resistors plus this parallel. And then that would be in parallel with the 2.5. And then that would be in series with 3.5, which would be in parallel with the 4.
Okay.
So it could have been really.
It could have been much easier.
But then we want a challenge.
All right, so we now have I1, I3, I5. Well, this one we should be able to handle.
So, with the I4, will we be able to put it into the, that 12 minus 15.2997 times I1?
Previous pages.
This one,
Go down to,
that one, 2,
Yeah.
that one?
Yeah.
Yeah, absolutely. Let's do it.
I got 2.0705.
All right, got at least one other person who got that. So now, I know in this bottom junction, I got 2.0705 coming down, I got 1.6503 coming from the right. Hitting this, it's got to, what goes in must come out, so we can now figure out the current flowing across the battery, and the 1 ohm resistor should just be the sum of those. So 3.7208. Again, not opposed to making a careless error there. And we have now found the currents. Well, actually, we haven't finished. Because we know the current's flowing across all the resistors except for the 1.5 and the 2 ohm resistor that we had combined.
What's that?
Look,
The 27/7 one.
that 27/7, we know that over this, through this branch here, we know what that current is. That's the 0.6490. But we don't know specifically what's going across that and going across that, because that current will split and then rejoin.
Does it matter?
Excuse me?
Does it matter?
Well, the question was, what's the current flowing across each resistor?
So,
That's
well, yes, it
between
matters.
you and your conscience, whether it matters or not.
Okay then.
I assume sadly you cannot just split that in half.
No, can't split it in half because most of the current's gonna travel the path of less resistance. So whatever we do, I know that I should have more going across here than across here. All right, before we do that though, let's do the voltages because it's gonna make make that split easier. We could solve for it, do another system of equations. I'm feeling like probably, let's just not do system of equations for the moment. Some bold color that's just gonna really stand out. Does this qualify? Sure. All right. I know the current going across almost every resistor. I know potential drop is, or potential difference is current versus times resistance. So my potential drop across here, if I'm going in this direction with the current, it's going to be a negative, so it's negative 3.7208 volts. Because it's 1 times, it's a 1 ohm resistor, so it's 1 times that.
Why
Well,
that number? Sorry.
Pardon?
Why that number?
Ohm's law, which I erased.
The IR thing.
So my potential difference is just the current times the resistance. I now know the current
Or the whole thing.
and I know the resistance. What about across that 4 ohm resistor? We got 2 ways to solve it. Pick one.
Wait, did we ever find I2? Did we need to find I2?
It's the
We don't have to find I2 because there's no resistors along there. But if you wanted to find I2, I know the current, I have 3.7208 coming in, I have 0.6490 coming out there, so this has to be the room, whatever the difference is. But, did you find it?
Yeah, it's 3.0718.
Which matches these two currents here.
you mean by like adding them?
Yeah.
Okay.
Okay, current flowing in, it's current flowing out. Current's not gonna, basically it's moving charge, we aren't gonna have charge sort of stored up in a junction. So what is the potential drop going this way across the 4 ohm resistor? Or how would you find it?
Is it 4 times 2.0?
It is. Did you do that already? An 8 point.
8.282 volts.
So what did we do to get that? Just
I times R. I know the current flowing across it, I know the resistance, just multiply.
so the 4 times that.
Yeah. Now, we have a way of checking this to see if we've done anything really horrible here. I also have that first voltage loop here. I gain 12 here, I lose 3.7208 there, I lose 8.282 there, and I come back to where I started. So, does that loss and that loss equal 12? Well, 3.7208, 8.2820, 820, carry the 1, 0, carry the 1. And we do have a rounding issue there. But it could have been potentially worse if we had taken currents out to 1 decimal place.
Is that an acceptable area?
Yeah. I'll work it out, I would have different techniques of doing it. And, you know, if this is actually a 7 instead of a 5, and you had a 5 there, I could have been close enough. On the lab, I would check to see where the problem is on the test or quiz. I think it's, again, one time in which there was a subtle difference because of careless error I made in making the problem. And it did make a difference, but we did not. All right, so what is the potential drop across this 3 ohm resistor?
Negative 1.977.
77? Yeah. Volts. What's the potential drop across the 3.5 ohm resistor? 2. 1977, 1947,
That's what I got.
1947.
Oh, I did 165 instead of 164.
Okay.
And then for the 3.51, got 5.77605.
5 point.
77605.
I got that. Then we got the 2.5.
What's the number under your name? Wait.
2.50325.
Is it always gonna be negative because we're,
If you're going in the direction of current, if I'd drawn the arrows the other way, it would have been positive.
okay.
On the last test, the last question on the second test, I asked for the potential difference across one of the resistors, and you were supposed to indicate which direction. So whether it's positive or negative depends on the way you draw the arrow. All right, so we still have these two resistors right here. So we need to figure out what is the potential drop across them. Now we got two different techniques to figure out this potential difference. I know the potential difference across the top path or the bottom path here is the same. They have the same junction at the beginning and the end. I know the current flowing into this section right here, but so I could do that current times 6/7. That's one of the techniques. Or I could do the loop here, and I start with 12, I lose 3.7208, I lose something, I lose I lose 1.947, I lose 5.77605, and then I'm back to 0. So whatever that gap is going to be the potential difference across here. I suspect the simplest is to do 0.6490 times 6/7.
I got negative 0.5562.
Negative 0.55.
Yeah, 0.5562.
I confirm.
All right, that is the potential difference regardless of the path I take. So now I can find the current, again, using Ohm's law, except this time I know the voltage, I know the resistance. It's just a matter of solving for current. So 0.5562 divided by 2 is some beautiful number. And so we'll get the current going across that.
0.2781.
And therefore the current going across this is, I could either do that divided by 1.5 or this minus that.
0.3708.
And again, we got some rounding. Looks like we're off by 10,000th of an amp.
What's the number below the 2?
0.2781.
Yeah, this is just ugly.
It is. And that is, at this point, everything else seems like child's play. Questions? Before I give you a simpler one.
So,
That's the first.
I'm confused. Okay, so when we got that, the negative 2.50325 volts.
Wait, negative 2, this one right here.
Okay, never mind. I didn't realize it was the same as 2.5 and then the 2. I thought the 2 ohms in the parallel.
The 2 ohms in the pair. Oh, yeah.
Yeah, I thought that was 2.5 ohms.
Oh, no.
Because of that line.
Yeah. So you can try to reduce it as much as you can. This is sort of the lesson of it. You can try to reduce it as much as you can, and then when you can't, you're left with the technique that I outlined. let's do a simpler one.
Now I'm gonna make it look easy. Didn't think I'd ever be able to say that one.
Yeah.
Don't even wanna erase it, do you? Just look so.
Yeah, well, at least it's recorded for posterity, assuming it's still rolling. Actually, since there's very little time remaining, let's talk about determinants, which is a math technique that some people find a simpler technique. All right, judging from the early reaction, people are not too familiar with determinants, or at least just shy about showing off that you've done determinants. A determinant, if you have an array here, so let's say 3, -1, 2, and 4. You're doing determinants. The way you indicate determinants is you put the two straight lines. Makes it look kind of like an absolute value, but it's not. You can start anywhere when doing determinants, but the way that I am going to go is I'm going to start in the upper left-hand corner every time. It is possible to do it without starting in the upper left-hand corner, but we'll just make it universal. We're just going to start there. So I write down that number in the upper left-hand corner. I now sort of mentally block out the row and column the 3 is in, and what I'm left with is a 4. So if I block those out, I'm left with a 4. Minus. Whenever you do this, when you go across, the first one's positive, then minus, then plus, then minus, then plus, and so on. Now I go to the next number, -1. If I block out that row and that column, I'm left with a 2. And now